And for that, I would like to call to the stage the panelist of the panel 2 session, Is Photonics a Semiconductor Technology? Please join me on stage, Gregg Bartlett, CTO of GlobalFoundries, Burkhard Slischka, CEO and co-founder of ALLOS Semiconductors, Ed Bailey, the General Manager and VP of Jabil, Martin Schell, Executive Director of Fraunhofer Hertz Institute, Torsten Vahrenkamp, the CEO and co-founder of ficonTEC, and the very well-known Ashkan Seyedi, Principal at NVIDIA. Thank you very much for having us. A round of applause for the next panelist. So let me start with you, Gregg. In your opinion, is photonics a semiconductor technology?
That's an emphatic yes and an emphatic no. And what do I mean by that? Okay, so, at the risk, GlobalFoundries is a semiconductor foundry, right? So, what's the phrase? If all you have is a hammer, everything looks like a nail. And I'll tell you, the first several years we were developing photonics technology, we were trying to make it look like a CMOS technology. And that works for a lot of it, but you need to deeply appreciate the aspects of a photonic, in this case, a silicon photonic solution that does not behave like anything else built in semiconductors. And it's all about, curvilinear shapes, germanium photodetectors, unbelievable levels of requirements for waveguide technology, resonators. There's a lot of things that don't look like foundry today. And if you don't appreciate the distinction between the two, then you're going to have a lot of trouble.
Gregg, allow me to ask you this. So a few years ago, you invested heavily on a quantum computing company, SiQuantum.
Yep.
And we just heard from Jabil that we are looking about ramping up to volume production quickly. What you did with SiQuantum really was incorporating new building blocks onto a fab to really enable single photon operation. What's the strategy? Do we want to accelerate quantum computers? Do we want to use those building blocks into other applications?
So it's interesting. If you think room temperature or data center photonics is difficult, imagine operating at single-digit Kelvin or millikelvin on there. And it just amplifies all of the challenges, right? Insertion loss, the link budget, trying to do single photon sampling is unbelievable. So we found two things. There are some aspects of the quantum solution that are very, very specific. Characterization of the devices over temperature down to millikelvin range is a key aspect. There's some other areas like the need for very thick waveguide materials of incredible cross-wafer uniformity, far beyond anything that exists all the way down into our 12-nanometer FinFET. Mm-hmm. And we've been able to leverage learning from the quantum solutions up into the data center solutions.
Let me get another perspective. Let's go to Burkhard Slischka from ALLOS Semiconductor. You are manufacturer of gallium nitride on silicon material. Is photonics a semiconductor technology?
When we look at the device, I would say certainly yes, right? We are using the same materials, we are using very similar manufacturing technologies, and with silicon photonics, of course, you have, by definition, the integration already. And even more, you talked before of overcoming copper. Photonics more and more take over functions which previously have been executed by electrons, if you want. So one field we are in is indeed doing materials for LEDs, and if any one of you is interested in talking about LEDs faster, catch me in the break. So from a device point of view, yes, clearly yes. On the other hand, of course, there are differences. There are differences in technology nodes, right? So rather micrometer versus nanometers. There are differences in wafer diameters, and that sounds trivial, but it's difficult to scale certain materials to large diameters. Some people like us, we are doing, again, on silicon on 200 and 300 millimeters. So a material which is traditionally used for LEDs is now coming on larger wafer diameters. Why we do this? Because our customers use silicon fabs to make LEDs for micro-LED displays. And they need to do this because they need the incredible yield advantages. So indeed, these industries are coming together more and more.
I believe that ultimately it's about the automation and the increased volume production. So allow me to go to one company that made a difference in Europe in the sense of manufacturing photonics-enabled modules with active alignment. I'm talking, of course, about ficonTEC. Standardization, automation challenges are there, but in your opinion, is photonics a semiconductor technology?
When we started that whole business 24 years ago, for sure it was not, because there was nobody talked about anything close to semicon. If we now, since the last 3 years, we get all the machines, or a lot of machines we are building, we get qualified for semi-standards. So we get more and more requests, okay, when you build a machine, make sure it qualifies according to semi-standards. When I see where our machines are located today, it's not semicon. If you see these typical assembly lines, our machines are always looking like the aliens because they are separate from everything else. And that is something I think we should definitely change as an industry. We have to fit into the lines.
Do you see a convergence? You think that we
Definitely.
should get there?
Yeah, yeah. And we're heavily working on with several manufacturers to make sure that we fit to, we say, common electronic manufacturing lines. And it has to change.
I believe, I'm looking, of course, at Martin Schell. We think about photonics as semiconductor technology. Do you think that we are a semiconductor technology, or do you think we should become a semiconductor technology?
I translate that into the question, is an Airbus 380 an airplane, and is a Piper Cessna an airplane? Both are airplanes, and both obey to the laws of aerodynamics, but the result, the final product, looks very difficult simply because the scale they operate on is a factor of 1,000 or 10,000 different. And so there's lots of parallelities between photonic chips and electronic chips. For example, the performance is made by the semiconductor die, and the performance is destroyed by packaging. So it's equal in both cases. Different is if you have a packaged semiconductor chip, 80% of the value add is in the die and 20% maybe in the packaging. And photonics is completely the other way around. It's 20% in the die and 80% in the packaging. And in terms of maturity, I would say the photonics industry is right in the Cambrian period of the main age, with the explosion into 20,000 different types, and this still has to consolidate. So electronics is a couple of 100 million years later and has already consolidated on the technical base much more.
This year at OFC, well, no, last year at OFC, you gave a great presentation, one of the best presentations I had in my entire life, about the fact that indium phosphide was the right material to take photonic integration to volume production. Do you still see that way? And in that sense, what can we do as a community to make that happen?
If you have a look at a single 6-inch indium phosphide wafer, it's about 100,000 laser dies, and each of these lasers can transport 200 gigabit. The silicon photonics have a big disadvantage in size if you don't count the inches, but the number of devices they get on a single wafer, right? So it's still open who's going to win.
Ashkan, this year at OFC, I never heard in my entire life anybody who has challenged the photonic industry as you did during the OFC. You were coming to us, telling us we need to overcome as a community some challenges when it comes to cost, when it comes to not so much power or losses, but it comes to manufacturability. Maybe you could tell us a bit about those learnings, and also tell us if, in your opinion, we should become a semiconductor technology.
So to answer your question of, is photonics a semiconductor industry, my answer would be, what the hell else could it be? But also at the same time, you could ask some questions grammatically correctly, but they may not make sense. So you can say, what does the number 5 smell like? And you think about that, and you're like, what does that question actually mean? So look at all the pluggables that could ever be sold in 1 year. It's tens of millions. So if you call that volume, and then you go to an iPhone vendor company who builds parts, they look at that and they're like, come on, man, that's not volume. I don't get out of bed for less than 6 zeros or 7 zeros. So I think that the punchline of looking at photonics and what it helps you do is the value add. It's an enabler. Simply put, you cannot build higher performance machines and ASICs and packages and generative AI training machines or inference machines without the use of optics. That by nature will drive the volume, that will by nature drive the value. So we have to, I challenge the industry to position optics not as yet another wafer volume play, how many connectors, how many pluggables, how many lasers, whatever. It's a value add. Are you bringing value? Are you letting someone do something they couldn't do before? That's it. If you can, you have a chance. If you cannot, good luck to you. Doesn't matter how many wafers you ship out there. So that's number one, is reposition the photonics as a value add and an enabler for what we need tomorrow. And what we need tomorrow, as you heard Luke talk about from the foundry perspective in some sense, AR, VR, sensing, the stuff that we do with GPUs and enabling co-packaged optics and high-density pluggables, that's like the last 20 meters of climbing Everest, okay? You have to do there's opportunities to do so much more down here at this base camp and this other base camp and then this other base camp before you worry about these high-end systems. Now, some of these high-end systems, quantum compute being my favorite one to pick on, which will never go anywhere. But from that, you can derive, it's like the NASA program, okay? From that, you can derive usefulness in other areas of technology applications. So working with, I saw Peter O'Brien in the audience earlier today. He's worked on these fiber connectors that can withstand the coldest of temperatures with water around them or other fluids around them and whatever. That's cool. That's a solution waiting for a problem, okay? And then the thing about the cost, I'm in my era of just telling people no, which is why I was asking the question that I asked earlier. I think this Cambrian era that was mentioned just a second ago, I think that's very good. We photonics people have an emotional attachment to, well, I think I can design a better grading coupler. I think I can save you 0.1 dB. I don't care if no one will ever be able to assemble it or it's $1,000 per connection. So you have to ask yourself, is it really worth it? Again, going back to full circle, does it actually bring me value to save that 0.1, 0.2, 0.3 dB savings in power? And a blank slate, yes, it does. But if it makes your technology non-manufacturable by the likes of Jabil and other high-volume partners, are you actually able to deliver that value? So I think by saying no to a lot of these wonderful ideas, figuring out, okay, this is the thing that we got to just like run this groove and get it to work, we can drive to standards. And the point that Matt was making earlier about this thing bouncing all around, it's not so much the transport or the frequent flyer miles, like Chris said. It's not so much the transport that sucks. What sucks is I'm vendor A, he's vendor B. I do my part and I give it to him, and then somewhere along the way it breaks, and then the customer's like, "Who broke it?" I'm like, "Well, I didn't break it. It was working fine when it left me." And he's like, "Well, I didn't break it. I mean, it just showed up on my doorstep. How could I have possibly broken it?" And then now you're stuck. That's the problem. And how could you do that? Standardized testing, outgoing, incoming inspections, defined, blah, blah, blah. The only way you can do that is by not having a Cambrian era, letting ideas die away. It's lovely that you can save me a quarter of a dB. Thank you. Call me in 5 years. Let's figure out how to make this awful solution work first, and then optimize once we have some grooves figured out. Long answer, sorry. Thank you for listening.
Thank you very much. I cannot top that, but I would like to go to Ed now. We have discussed with Matt Crowley before about the need for volume production, and for that we need to scale up photonics. And for that there are certain lack of standardization and lack of ways to address those challenges that come when you take something to very high volumes. In your opinion, what are the main challenges that we're having in scaling photonics manufacturing?
Well, look, I think you just touched on a lot of the good points, right? I mean, at the end of the day, we think in terms of things as, when we start driving these processes, first you got to really industrialize the design, right? And you think in terms of, we talk in terms of standards or standardizing, but if you don't design it for scale and you don't drive that process, we talk about kind of shifting left, in the design process, you can have the greatest design, greatest performance in the world. If it's not ready for industrialization, you have no hope of automation, you have no hope of scale, right? And so understanding the requirements, what are we trying to solve for? Obviously, we're driving a technology solution. We need to understand what's the price point, right? In Matt's presentation, we were talking about that, someone asked the ASP question. Really, what's the inflection point where this technology becomes adoptable and it makes sense to replace copper? I love what you've just talked about, right? If I think in terms of what we're talking about today in photonics, I also liken it to something else we're heavily involved in around liquid cooling. Some of these technologies were kind of nice to haves. They have been previously about maybe an efficiency statement, maybe a best-in-class statement. Now they're really about capability enablement. We're getting to the point where we have to have them for the rest of the system and ecosystem. So if we want to drive that scale, we need to make sure that we're defining what we're solving for, we're defining the price points. As a community, we're engaging the right partners at the right point in the process so that we're enabling that design to be industrialized and then enable to scale.
Optical staff is around here. Whenever you have a question, please raise your hand and the microphone will come to you. And now I have to address another topic, which is the photonics packaging. We've been talking about photonics packaging as a challenge already for many, many years. But now we are hearing it every year at OFC, 200 gig per lane. This year at the ECOC we saw a demo, 400 gig per lane. Actually, RF is becoming part of photonics packaging. And I would like to see some of you, what are your views on that, and how do we need to address the RF community and bring it closer to photonics, because it looks like we need it. Ashkan, starting with you, is in those high-speed applications, what are the current challenges of bringing RF to the photonics industry?
So nothing is new. It's just that people retire and then young kids like me forget what was done 30, 40 years ago. And so you think you have a new idea, but then you talk to someone and they're like, oh, we did that in the late 70s. So the value add, and this, I can point to a clear example from our own company, the value add in capabilities of systems and of packages is through multi-chip packaging. That's why your cell phone does what it does. It's 50 different companies with 40 different chips inside this tiny little box. We showed that moving from our Blackwell or our Hopper GPU into Blackwell, you build a bigger chip. It's 2 ASICs, 2 die talking to each other, high bandwidth memory, interposers, and the cooling. So amalgamation of various parts helps you bring more value. So when you do that, then if you're a mechanical engineer who's working on reflow and fiber attach and thermal management and warpage, you have a very good job security, because as more of these high power ASICs get integrated together, this is where you can deliver that goodness of the value. So your question was RF into photonics. It's all about signal integrity and minimizing and eventually eliminating the electrical channel. Digital compute will always be there, but then how can you turn that signal optically as soon as possible? And the vision is, look, if you could build a hyperscale data center or a supercomputer where the optics and the networking and the I/O were completely free, you look at the entire power savings and you're like, actually, that's still a lot of power because compute is pretty expensive. But if we can get to a place where optics and interconnects are effectively free, which is what I was saying at OFC, then what could you build? And let's work towards that. And high-speed integrity kind of goes away if you can eliminate that high-speed channel, thereby requiring advanced packaging.
Indeed. Actually, 2 weeks ago, I went to Denver, Colorado, and I visited Lightweight Logic. And I was really surprised on how much a company has invested on RF testing.
Yeah.
However, last week, I went to ECOC, and I said, where are the microwave photonics companies? And they are, of course, they are a European Microwave Week in France. So we tend to have a problem here of bringing these two communities together. What's your take on that?
So much about technology application and adoption in the market is about storytelling, understanding what it is that you do, what are you actually good at versus what you think you want to be good at, and then who needs that capability, and how do you align these interfaces between what you do and what someone else does and what this other person does. So the analogy is like, I have a really good cattle farm, and like I could make really high quality beef, but how do I sell that as burger patties? Well, you need someone in the middle who's like, hey, they care about organic, grass-fed, humanely treated beef. Why? What does that mean for your health? So you got to completely close that loop. We try, and I try with the platforms that I'm given, thanks to you, to try to illustrate that whole story. To try to say, hey, yeah, if you do save me 1 dB on the coupling loss, what does that mean for 130,000 GPUs and a giant building? If you can close that map, hopefully you see the problem that we deal with end to end, and you understand why I don't care about the 1 dB that you're going to save me, because it's going to be 10x more expensive. So as more people get educated and they understand where their piece fits into the bigger puzzle, they can help close these gaps. And I will say this to anyone who is thinking they have a solution that can work for anyone on stage or everywhere else. Please approach the conversation with a lot more open-minded, rather than saying, you should just buy what I have is ready to go. Be like, hey, I'm really, really good at doing this. Do you need this? Does it help you? Again, find that value, not look for the PO, basically. Help me understand how what you do maps into the problems that I have, which are millions, and then we can find a symbiotic existence here. It's a small world, fragmented world. I feel like also so much of the conversation today is around integrated silicon photonics, but lasers, 3.5, making a reflections insensitive EML so that I don't have to have an isolator. EMLs are shipping by literally the millions across the planet today. Solve that problem. That's a photonics problem. Solar cells is a photonics problem. CD burners, CD-ROM players and DVD players is a photonics institute, right? The reason we have silicon germanium is because CMOS used germanium, and we just happen to pick that up. Everything is interrelated. Everyone works for us. Everyone works for us in the photonics industry. You can pull from all of that, but always find the value. I challenge you to do that.
I believe we already have some questions in the public. Please remind us your name and company.
Steve with Vanguard Automation. So my question, let me just first start out with a description of silicon photonics, which is supposed to be CMOS based, but you need germanium for the photodiode, you need silicon nitride because the waveguides are high loss, you need undercutting, you need to do etching for V grooves, and now you're at the point where a Mach Zehnder kind of peaks out at 200 gigabits per second PAM4. Where do you go with silicon photonics? What's the future of that? And Gregg, you're probably the best person to answer that.
I'm happy to start. So you properly identified all the challenging aspects of, today our platform is 100 gig per second. We know that 200 gigabit per second is there. I do think it's going to be moving from single lambda fibers to CWDM followed by DWDM. Of course, that puts a lot more challenges on your modulator designs and performance. You got to get from today our POR is 35 gig on the germanium photodiode. We know that we need to get to 65 to 75 gigahertz. So I think it's going to be moving into the DWDM domain as the only long-term approach to the overall bandwidth.
Any further questions? I want to continue with you, Torsten. You have identified one of the biggest challenges of the photonics industry is the fact that we need better wafer level testing. At some point, photonics, as it was defined, and I don't necessarily agree, by Maria Marcet this morning as a promising technology, we need to address the yield, but we also need to address the way that we test. And for that, we need to work closer with the RF community. How have you defined the business of ficonTEC into solving that particular challenge, and what is your preferred future in that respect?
So on the wafer level testing, there's several platforms which are already very standard for the semiconductor industry, for the pure electronics part, but there's not a specific machines for the optical part. So that is actually what we are tackling from ficonTEC, and we just had a very interesting discussion with Louis Raphael from Femtum, where we kind of will cooperate in order to build machines which are actually finally also able to trim the wafer. So I think there's a lot of things going on. We can work when we work together, when we are collaborating, and we understand the problem of each individual party in the whole value chain.
So you're talking that not only you can test the wafer, but you could potentially fix
test,
errors.
trimming, test. Actually, where we can then tune the Mach Zehnder's on the wafer.
Gregg, this is what comes to me in my mind. If you are thinking about incorporating photonics to semiconductor fabs, there is so much effort in testing. We saw the diagram of Jabil, we saw the business of ficonTEC. Is that photonics is not mature enough not to be reliable, and we need to test and spend so much money in testing? Is that the challenge that we have now?
It is indeed a quite significant challenge, and to use the term that Matt said earlier, right? There's a lot of snowflakes right now. So every time you're trying to figure out how to do testing on there, once you get beyond insertion loss measurements and modulator frequency performance and into full-blown optical circuit functionality, it's an area of the largest investment we're making, as we've realized that our customers are asking us increasingly to align with them on a test strategy.
And what are the 2 or 3 main challenges that we need to solve ASAP?
First of all, as said, complete lack of there being, industry standard platforms for test. We've been doing optical testing for a decade in GF, and today they're still homebrew tools. Right now, the inline optical test, finally we worked with Keysight to be able to commercialize their existing platform, but for the functional testing, those don't exist.
And why not? Because we are really good at standards in photonics. We standardize the single mode fiber, we standardize connectors. Why couldn't we standardize this?
Same reason the OSATs don't have photonic assembly capability, because the demand is not there. Tell me you got 30, 40, 50,000 units a month, you start getting people's attention. But when you're still in the early prototyping phase, you just don't get the investment.
We got some questions in the room. Please remind us your name and company.
Hello, I'm Ali from TNO. I have kind of 2-part question. One is, why do we want photonics to be a semiconductor technology? I wasn't here 50 years ago when semiconductor started, but probably it wasn't cheap, it was probably expensive. Or we know it was more expensive than the other solutions. And that takes me to the second part of the question. Why don't we take photonics to be kind of the high-end, expensive solutions? Because we're competing with a huge giant that's called semiconductor.
Who would like to address that? Should we stay in niche markets and charge high prices for low volumes? Martin.
First question, why do we want to be a semiconductor technology? Because all the photonics people believe that if they transfer their processes to semiconductor technology, they achieve a yield of 100% and they achieve 300,000 wafer starts per year from a similar fab. If this would be the case, then the testing industry would not exist. So some photonics people have some very optimistic, too optimistic imagination about photonics in semiconductor technologies. The second thing is, if you restrict photonics technologies to high end, it's very nice for HHI, for example, but it's very difficult to feed a company with the already small volumes if you cover the whole photonics market. And if you then restrict yourselves to the high end, it's very difficult to utilize the equipment you have. So it's a nice niche, but for industry, it's very difficult, I would say, to feed a company with that.
Did he answer your question? Any further questions in the room? I agree that there is a lack of standardization. I agree on that. But Ed, you have in this presentation by Matt, I could see a spot of testing in Europe, and I believe testing in the high volumes that Jabil is looking at needs to be standardized. Is it happening that companies are doing the standardization themselves and not sharing it with the community and not making industry broad standards?
Well, look, I mean, there's certainly a lot of companies that are out working on their solution or their design, when we see that often today. And that's not just unique to this industry, right? But in our experience, that's, again, it's going to limit scale. It's going to limit getting to the price point where adoption's going to be mainstream, if you will. And so we see we certainly see a lot of people working on their solution, their optimization. Maybe it's their point they believe of differentiation. We frankly don't see a lot of work around the standardization. And look, I think where it's going to come from at the end of the day is the pressure in the marketplace from the end customers. The customers that know that they need this technology in order for their solution or their value to get to market. And just like Gregg mentioned, once you see the demand is there, then all of a sudden some degree of standardization will occur. It's going to be whoever drives the volume first is inherently going to drive the standard.
I try to not say anything, but I'm going to say something. It is not volume. It is the crux of it is no one wants to give up their IP. That's it. Okay? No one wants to give up their IP because, Gregg, you got a top silicon that's some thickness, and you have a grading coupler that you like. And Luke's got a different top silicon thickness and a grading coupler that he likes. And Torsten's got to go make a standardized tester. And so, okay, he asks, hey, at 1310, is it an 8-degree emission angle? Is it 9 degrees? What's the reflection like? What's the polarization sensitivity like? And you're like, well, it is the way it is. I don't know. What's the Rayleigh length? How far do I go? Oh, well, it's proprietary. Someone else paid for that grading coupler, blah, blah, blah. Like, come on. It's just a grading coupler. I don't want to see the apodization and the chirp of your teeth and the etch of the grading coupler. Just tell me everything else. Tell me a mode profile, tell me the emission angle, tell me the polarization sensitivity loss, the emission angle, blah, 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 so I can go and say, hey, if it's 1 dB or less, it's a good one. If it's 1 to 2 dB, it's a bad one. And that's it. And so you got to put a little bit of that skin in the game. I mean, that's like saying, hey, TSMC and Samsung, you have a proprietary micro bump. TSMC uses 160 micron, and Samsung uses 158 micron bump pitch. And then now you got to go design 2 probe cards. And what the hell, guys? It's just 2 microns. Can't we just align on one number? So the opposite of the question is, why do we have electronic standards? Because these fabs and these OSATs realized, I'm not going to differentiate and derive value from the hardware. It's just a testing interface, and a rising tide lifts all boats, so that if I just agree we're going to both equally have shitty gradings, but everyone can test them day in, day out, all day, and get a 1 sigma variation, a 6 sigma variation that's the exact same, great. Then we all can at least move product out the door, and one guy can build 1 testing script and 1 alignment algorithm. Right now I have 2 different grading couplers and then 4 different connectors. So that's a matrix of 2, 4, and then another 4, and then his machine's got to go figure out how to align 8 different things. It's like, holy cow, why? And they're all, by the way, the best case scenario, all within 0.1 dB loss of each other, and everyone thinks that they're the snowflake. It's frustrating. For 10 years, this is the frustrating issue, right? So that the crux of it is the emotional detachment, and let some IP go, and share some of the know-how so we can all say, okay, now it's the same thing. Right? Sorry, one last one. The utopian place I want to get to is, without knowing what the physical structure looks like, to say that his grading and that other guy's grading are the same. Statistically, they're the same. Oh, man, that'd be beautiful.
I can't agree more. So why do you think whenever we go to a foundry, any foundry, so not only
He's on stage, so we're picking on him, yeah.
But I go to Smart Photonics, or I go to IHP, or I go to any foundry. The first thing to tell you is, here's the PDK sign and NDA. Why there is such a, in your opinion, I'm going to ask, of course, Gregg afterwards, but why there is such a protection about the building blocks themselves?
Because they've paid out the nose for it, and they think that that's where their value is. But it's not. A PDK is an enabler. It's an enabler. We will give you the GPU for free if you will pay for the software.
Your life.
Right?
Gregg, you're desperate to say something now.
So I think Ashkan is giving a view of the world we are today, but I actually agree with Martin's statement earlier. This is a discussion about the Precambrian period. Just think back, and I've long since forgotten when IBM invented C4 bump technology. That was a damn differentiated technology when they invented it, because they were able to do a pitch and reflow process that didn't exist. Today, how much drama is there around copper pillars and tin silver? It's not. The industry has ramped to volume. There's no differentiating. Of course, you're always trying to drive smaller bump pitches and tighter copper pillar, but everybody's doing the same things. They frequently land on slightly different pitches just because there isn't any standard or roadmap.
So why did IBM let that go?
So this is the key point for me. If you look back in that era, those things that differentiated then no longer differentiate. So today, you're right. Everybody's grading coupler, everybody's fiber attach process is out there.
It's pretty vanilla. Yeah.
And let me use the example that I think volume does matter. When Intel announced their Tri-Gate, 15 years ago, the industry went, that answers the question between fully depleted SOI versus FinFET as the volume driver. They literally, because they drove that volume, standardized what the industry adopted. Silicon photonics, I agree with you that eliminate the non-differentiated misalignment that exists, but a volume driver is a really loud voice that flattens a lot of those discussions.
Yeah, you can't deny brute force. Even if the technology sucks, you can't deny brute force. What I'm saying is, you'll never have that magnitude of volume.
You saw the original Tri-Gate when it came out, right?
Yeah.
It was not a
I mean,
pretty
with
thing.
photonics, we're never going to have that kind of volume, ever. Even if you consider all the use cases of sensing and all that stuff, it's just not going to be.
It's never going to be high volume wafer manufacturing. It will be extremely high volume component manufacturing.
Okay. I mean,
and to Martin's earlier point, that 75% of the bill of materials is after the wafer leaves the factory.
So could we agree that if you eliminate the differentiation things that help you bake components, we can drive volume?
I think that's a big part of it, yes.
Hey, so that's the interfaces, right? The electrical and optical interfaces. So go design whatever modulator that you want, but couple to it all the same, so these guys can, can test and build modules all the same, because he doesn't care what's in the silicon. He just wants to stamp them out.
Agreed.
Agree is nice, but what do we do now? Do we take somebody from Tower here? Do we get anybody here and we say, okay, let's share the PDK? Do you think that's realistic today?
Well, that's unrealistic. I'll just go on record saying that today. Having said that, you know, ITRS was driven by end market customers, right? Yes. That these were IDMs vertically integrated, or the Qualcomms of the world that drove enormous volumes on there. Never underestimate the ability for NVIDIA, AMD, Intel, Broadcom to be the four elephants that said, we want all of you guys to align on these 5 things. Then we'll go work on our modulators and our waveguide materials, et cetera, and differentiate those technologies for superior performance and in particular cost, but it would remove a lot of the ambiguity and uncertainty outside of the wafer if in fact there were more.
We try to do that by speccing the effective price point. So if I want optics to be 20 cents and a machine is $500,000 and the best thing you can do is 30 units per hour, you're never going to get there. Then you got to say, why is it 30 units per hour? Why does it take 20 seconds to do this thing? Oh, because I got to get all my 16 fibers in the V groove just right and zap, 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 and cure them all. About, oh my gosh, should I be doing something different? Go figure that out. I mean, we don't want to be too descriptive, and at that point, do that magic to figure out how to make it reflowable, how to make it scalable, so you can go from 30 units per hour to to 150. I think that's pretty realistic, to be able to amortize better.
We have some questions in the public, but then I'm going to come to you with that comment. But Michael, tell us.
Michael Levy, Lightwave Logic. Gregg said something that really sort of got me thinking. It's the C4 from IBM, which happened in the 60s. I mean, it was differentiated. So the question is in the electronics industry, we've had a very, very successful CSP, chip scale packaging. Basically, throw away the package. So if you think about photonics, historically, we've had gold boxes. There's been some innovation around trying to get rid of gold boxes. What does the panel think about chip scale packaging for photonics, just not having the package at all?
Who wants to address that?
I'm not sure I understand the question, Michael. I mean, you're going to have optical chips somehow touching the ASIC in the digital domain. So bumps and fiber attach is all you got.
We're not going to have a gold box, right? So you're going to have maybe a PIC chip or maybe a couple of PIC chips. You're definitely going to have fiber attach of some kind, and maybe you'll have some bump in or pin grid arrays or some type of interposer. But it's not going to be a gold box. It's going to be something that's more electronically aligned. It's sort of where I'm coming from.
Yeah, I mean, even the EML business today, it's all wire bonds on a very nice ceramic COS. That's why they're expensive. So this integration play, I mean, your question earlier was, why do we want to be silicon integrated? Because we're going to be integrating. EML functionality, you just give it a supply current, and you have a backside monitor, and that's all you get. Integration gives you monitoring, gives you health of your links, health of your optics. You can do exactly this, build a large interposer that talks optically between various ASICs. That's why you want to be semiconductor-based technology, because you can derive value. Piece parts, optical benches, micro lenses, isolators, focusers, that kind of stuff. It's mom and pop shop. You're never going to trigger volume and deliver value, because you're always going to be too expensive.
Torsten, we have semiconductor fabs manufacturing photonic integrated circuits. We have large companies bringing them to the next generation AI challenges. And we have companies offering packaging solutions, like, for example, Fix here in the room. The automation that was addressed just now by Ashkan. They were talking about high volume, but we have machines that only package certain small units. How can we accelerate that? Because at the end of the day, you are one of the market leaders, and you're a company with how many employees?
We're now in total 250 people.
Correct. Yeah. How can we accelerate that?
Working together, finding exactly what Ashkan just said, understanding why it takes so long, whereas still epoxy, which takes a long time to cure. We have the delicate fibers to handle. We grew quite a bit with a very customized tool. So it was actually how we made good money over the last years. But actually what we have to do as a company now, as ficonTEC, we have to say no. No to all the different things, beautiful, wonderful, weird and wonderful packaging methods. And that's what my team is heavily working on. What we did is we did a map of all the transceiver packages and the co-packaged optics we did over the last 3 years. We put them next to each other. We built a machine out of it, and this is like a standard tool now, which we can go to customers. But it's actually, it's like, up to now, we are like, our customers were driving high speed through the fog. We saw the backlights. Now we overtake, and then finally we don't see anymore where the industry is moving to. So it's actually not our expertise to tell the customers, okay, that's where you need to go. But I think we have to.
Do you see a shift in our photonics industry? Because I saw the presentation by Luke and the Hoven today, and photonics was a layer in a semiconductor manufacturing line. And for many years, we're taking a photonic device, and we have aligned a fiber next to it. We have controlled the temperature. Tomorrow, we'll see great things from Peter O'Brien. Do we see a change in the mentality of packaging, in which we go more into less packages in the CMOS perspective?
Yes, so we're moving away from this individual packaged device to the co-packaged optics, which completely changes the machine layout. So that is, and the players are different. So we are talking now really to big CMs instead of to a larger number of smaller players.
Has some questions in the public. Please remind us your name and company. Yes.
No? Yeah, so this is Íñigo Artundo from BLC Photonics. We have been providing test services for the last 10 years or more to the photonics integrated industry. And I agree that standardization is really a must. We are working with software companies like Lucida or Synopsys to have some level of standardization of the layout of the photonic circuits, not to have the NRE cost for testing escalate into things that are not acceptable for industry. And we have been working very closely with ficonTEC also to standardizing the wafer level testing tools that you need for that. But I think maybe this is a request for you, Jose, and for the whole optical community, because we need more people like Ashkan, actually end users that are able to tell us what is really needed, because most of us here are technology providers, but of course without this kind of road mapping driven by end users, we will never be able to push this standardization forward, and this is also needed on the foundry side as well. So this is just more of a comment, right? Trying to push the end users who are actually driving the applications and the markets to really sit down with us on road mapping tables to really drive the road mapping of all these technology providers forward. So, yeah.
I do agree, and having Ashkan, having more end users in the room is mandatory. Now that you have the microphone, you have been designing for many, I would say almost all the foundries of photonic integration in the world. Is it true what Ashkan just said, that the difference between building blocks between similar foundries and materials is small? Is it easy to adapt a photonic design from one foundry to another today?
Unfortunately, Ashkan is right. There are plenty of differences on the PDKs, and not only between different material platforms, because we are talking here about silicon photonics, silicon nitride, indium phosphide. Now we have contenders like thin film lithium niobate, BTO, polymers. So this complicates very much the design work, but not only that, the software implementation into different frameworks of the PDK at every foundry also makes it more difficult. So if you really want, as an end user, to port one design from one foundry to the other to really drive volumes up or have double sourcing, it's really mission impossible nowadays. So it really requires huge investment and delays in delivery times.
I'm curious about...
So just a comment, that sounds like it is missing the equivalent of a TSMC, a dominant player, who's actually setting the norm, because in my understanding, in silicon semiconductors, TSMC has their PDK and every other foundry needs to think about how to fit into that. So that actually this transfer from one foundry to another, it becomes much easier. So the dominant player sounds for me like is missing.
So we're conflating a couple of things, right? Porting processes requires a level of abstraction. When you port from Samsung 4 nanometer to TSMC 3 nanometer, you have no idea what the gates look like. You have an effective VLSI or Verilog A model, right? That lets you say, well, look, this transistor and this transistor the FTs are slightly different. Like you have a test bench, you pop in their components, you pop in this other person's, and then you look at the results. That level of abstraction definitely not there for optics, because first to do that abstraction, you need volume data and blah, 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 blah. Companies like his exist because fabs can't test. What he gets paid to do is check their stuff. And then when I test that grading and it sucks, and I'm like, Gregg, the grading sucks. He's like, sorry, it met my process standards. What do you want from me? I'm like, okay, well, this is the problem. You just sell me a wafer and wish me luck, and then I got to deal with it. So actually, you need to buy him and put him in your fab, so that all I get from you is a known, good, qualified PDK. And then what I spend my money on doing is functional testing, ADST, Adman test, that where you have no idea what's my circuit. It's like the prototypical example is a PLL. I design a PLL, phase lock loop, the way I want to do it. But I need TSMC or Samsung or Intel to tell me, did their resistor, inductor, capacitor, whatever, hit spec? They have their own test keys. They test all that stuff. They give me that report. So when my PLL doesn't work, I look at the process monitors. I look at the PDK component test results. And I'm like, yo, fab, you are absolved of your responsibilities. My designers are a bunch of idiots. I go choke their neck. But if I don't have that, the designer's like, hey, man, I designed it right. The fab sucks. And the fab's like, hey, man, you designed it wrong. My process is good. And I'm stuck in the middle. That's the real problem, right? So porting is a very simple statement to make, but there's a lot of complexity under that we're still not there yet.
You had to comment, Gregg. You cannot just leave it there.
I just met him yesterday, and Gregg hates me
I
already.
think I just got M&A advice a minute ago.
Honestly, right? And I mean, your point ago about standard footprints, that's spot on. Absolutely. That's a huge bottleneck.
We have some questions in the room and only 5 minutes to go. So they're all the way in the back. Please remind us your name and company.
Tolga, Fraunhofer ICM. We do see in the last years that photonics coming to the interposer. So is it a case that photonics becoming kind of packaging platform for high bandwidth microelectronics?
Absolutely. To me, it is. I think optics is just another very good scalable transmission line. You got to think about it like that. It can be a transmission line on the chip. It can be a long distance wire with fiber. Right? That's the holy grail.
We have more questions. Please remind us your name and company.
Alex from Inalum. So we're doing lasers, and it seems like an active device is a big issue when you compare it to copper because it's less reliable and so on. So my question would be, do you think systems like WDM systems to reduce the amount of active devices we use is the right way to go to reduce the issues with the reliability and so on? Thanks.
I'm talking too much. Somebody else take this.
Go ahead. You want it.
So I think WDM is going to struggle for two key reasons. And the flip side of that is you have to ask yourself, why do we have high-speed SerDes? We have high-speed SerDes because, as you just very clearly heard, we had 160 micron bump pitch C4 70 years ago. Nothing has changed. Metallurgy sucks. It doesn't get smaller. So the only way to increase stuff is to just shove more bandwidth density. So if you come to me and say, hey, what used to be a 200 gig single diff pair, now I want you to make it 8 diff pairs running at 25 gig or 32 gig, I'm going to tell you, can you give me a package that's 8 times bigger? Because I'm going to need 8 times the number of diff pairs. And then go talk to all these folks who make organic interposers, silicon interposers, and find out that the cost at 50 millimeter on edge to 60 millimeter on edge to 70 millimeter on edge is like this. So no, it's not tenable. Not to mention all the other stuff you got to do in the optical domain. But just from a bandwidth density perspective, we're not there yet. Packages are too expensive at the sizes that you would need in order for me to be able to build a 50 terabit ASIC.
Martin, would you like to comment on that?
So I'm a bit more optimistic about WDM in that application segment whenever shoreline densities plays a role and you have simply a problem to get too many optical interfaces on a given centimeter of space. And on the other hand, as far as I know, all optical technologies which are capable for DWDM, DWDM would require temperature stabilization on a 1 degree level. And if that would be possible, I mean, that would open up completely new room for optics. But I'm a bit skeptical about that.
Yeah, I agree with that part too, to pour on more bad news.
Let's finish with some good news. We have
come on.
2 minutes to go. So I'm going to go through the panel now, and I would like to ask you, when we had the Global Photonics Economic Forum in 2030, somewhere here in Malaga. What would be your preferred future? What would you like the photonics industry to look like with respect to semiconductors? Let's start with you, Gregg.
Well, very simply, to have successfully made the transition from SerDes copper and electrical into the photonics world. And that's a statement about pluggables, certainly co-packaged optics we expect to be in very high volume manufacturing. But the dream is there's an ecosystem of partners that have aligned on things that don't differentiate a product, that allow equipment providers to make lower cost, high throughput, highly automated solutions. And I think, given the significant cost associated with the post-fab processing, that's really where the work needs to be done. By no means am I suggesting we got everything licked at the wafer level. There's still lots of work to be done, but we need industry-wide effort convening to drive the cost down.
Torsten.
So my vision is having our equipment fitting into standard electronic packaging lines, no touch points anymore, no manual labor in between, blister in, blister out, fully laser marked, so fully automatic lines with photonics packaging.
Ed?
Yeah, we've had some discussion on interposers and co-packaged. I think a lot of this stuff, not just at the wafer level or at the optical component level, really at the system level, right? I mean, today we build, we'll build 30,000, fully integrated hyperscale racks a year. We're building stuff for automotive, a lot of other industries, and it's not just about the testing post-wafer. It's really the testing of the system. And oh, by the way, the systems are getting much more complex and much more expensive. So, I'd like to see us, as we really get these things integrated at the system level, the opportunity around obviously latency and power, throughput, and then really optimizing the test end-to-end. It's a significant opportunity for our customers in the end market. So I'd really like to see the community come together and see us go whip this thing, because the upside's significant.
For me, it's actually a dream having Jabil talking about photonics like this. It's actually, for me, you just made my day, the two of you, really, honestly. Martin.
I don't have a vision, but I have a dream. So my dream is that the CTO of Coherent, the CTO of Lumentum, CTO of NVIDIA, GlobalFoundries, and Google, Facebook, they notify this discussion here. They sit themselves together, start some standardization activities on optical submount level for co-packaged optics, and next year they sit here and report about their progress.
That's not a dream, that's a challenge. Challenge accepted. Burkhard, what's your preferred future?
I like that as well. Well, I have actually a wish list. So on the one hand, I have a wish list on the to the foundries. I think you guys need to figure out how to handle low volume and integrate them and still generate value. So going back to Michael, I think it's Michael's question of Michael, right? Of wafer level packaging, for example. You can do this today. You can do a back plane for a micro display. You can make a front plane. You can make a wafer level bonding. Everything wonderful, and then and you can do this only in a quite advanced 300mm line. But you guys would adopt, and your colleagues would say, oh, the volume is too small. So we need to overcome that.
Ashkan.
I imagine a scenario where fermions and bosons can intermingle, and the transition of information from one to the other is seamless. So electrons, photons, and phonons can kind of mingle and live together. So you can do optical communication and optical compute heterogeneously inside of a package. If we can get to that state, then we've been as successful as physics, the laws of physics, allow us to be.
Wow.
Nerdy answer, but
He asked for a vision, right?
Yeah.
That was awesome, wasn't it? Well, the coffee break is now and it's the most important part of this event, so enjoy it.